Very good morning, friends. I am here in Los Angeles, and I am coming to present for you about the subject matter of how to get more work done with less effort, better results with less effort by using the generic programming paradigm. And I am also in the company of two very nice friends, Jamie Pond, and someone that you might know from prior presentations, Scott Bruce, because we have collaborated before. Each of us will have a section in the presentation. Of course, that mine is the longest, but yeah, I'm going to delay the introductions for a bit later when the opportunity arises so that we can get into the material as soon as possible. However, I want to be very clear that my opinions, the opinions that are going to be communicated here are my opinions. I do not claim to represent Scott and Jamie in that regard. If there are mistakes in this presentation, they are going to be my mistakes. I am fully responsible. And if there are successes, it is their merit. Okay. So the objective is to get empowerment, which I wanted to mean achieving more, better quality, better performance, uh, more understandability with less effort on our part. How are we going to do something that sounds to be impossible? Well, um, what I'm going to be doing is to provide you with guidance to express more knowledge into source code because I have the very firm belief that that knowledge composes exponentially is at the root of how to do great software. So the more knowledge you put into software, the easier it is to leverage it and the further ahead you get. Okay. So, thank you very much, Jim, for giving me the branding. I absolutely love the branding. It's compatible with the colors that I use for my presentations. And what I have shown you until now is that we're going to be achieving more with less effort. And that sounds impossible, but all of what the three of us are going to be doing today is to provide guidance so that you can study, so you get your own empowerment. And I believe that the selection of guidance points that we bring for you are going to be very useful for you. So I was saying that we're going to get guidance about, we're going to share guidance with you about the successes of genetic programming, which in particular showcases how to take advantage of well-established concepts, how to refine them, um, what is the meaningful participation that you can have on listening to criticism of well-established concepts and the evolution of the language and the solutions that other people are working on. Um, we're going to be talking about failures that happen when the principles of genetic programming are not there, either because they could, but the authors chose not to use them, or because they couldn't, like in the Java programming languages, that it's nearly impossible to program in a genetic programming paradigm way with the Java programming language. Um, and one thing that I hope is going to be very novel for you is that we bring for you, the bulk of what we bring are demonstrations of generic programming concepts being made. I am not claiming that we are the only ones who do new generic programming concepts, but there are special ways in which the work that we're doing has like a shorter time frame than what other people are working on, and this is going to be explained later and why is that and so on. And I believe that this is the most distinctive, the place where we can put the most value for you in this presentation. Okay, so why us, los tres amigos, the three friends? Well, we have consumed our own dog food because we have applied the things that we come to share with you has good practices and ideas and methodologies of how to do things, in particular the genetic programming paradigm, at previous jobs that have the scales of Google, and in particular myself at Snapchat. Scott and I have been co-workers were co-workers at Snapchat. And as a matter of fact, Scott is the person who brought me into Snapchat, sorry, into Snap to make a Snapchat. And that's sufficiently large scale for the successes to be significant, right? Um, you know that I have been working on this Zoom repository for a while now, and I have been sharing with the community my findings and the successes that I have had and how I got to them. And today we're doing something that is special because this is the only time that I have released to the public a production strength library, which is the SWAR library. So I consider that at this point in time, the part of the SWAR repositories that concern to the SWAR library is ready for massive production use, and it'll join the type erasure framework. Just as the type erasure framework was acquired production strength in an organic way because it was used in production before it was released to the public. This case is the opposite. And one of the differences is that because we're doing a release right now, we bring uh, uh, demonstrations especially made for you, the attendees of this presentation, so that you can immediately connect to the interesting features that the library has. So these have been thoroughly benchmarked, and I hope that you're going to agree with us that the code looks simple, and we're going to show you that the results in terms of performance, for example, are much better than what large teams have been doing, presumably doing their best. Like I said, you're gonna see genetic programming concepts being made, and Scott and I have the help of Jamie that is gonna bring uh, the complement of a fresh perspective, because Jamie is a newcomer to our group, to our repository, and I'm very enthusiastic about what Jamie has been doing and the perspective that he can bring to the topic, because he's one of those who is hopefully getting empowered, right? So it's like an early demonstration of what happens when you begin to put these things into practice. Okay. This is different to my prior two presentations because we're gonna see lots of code and Godbolt and look at the assembler and gain lessons from that, which means that we have to buckle up because we have lots of material ahead of us. The time is fine, but we had to use it efficiently. So in the way that we're doing it. So Jim, any problem that you detect, you let me know. And during this presentation, I really love the people who make the allowance of time to pay attention to a presentation. So for me, it's very important the questions. And when my collaborators are presenting, that's going to be an opportunity which I'm going to go with Jim to see the questions that you might have and see if I can answer some of them while at the presentation itself. And very much thank you for your feedback. It's really informative for us, especially when we are presenting online that we don't have the faces of people to understand what's going on. Okay. I'm going to drop a false lead into the presentation, which is the electromagnetic wave progress metaphor. And if at the end of the presentation you know what this means, then you're going to have the placeholder to really connect everything together and go home really understanding what his presentation was about. But I am not going to do the great reveal just now, but when I think that the time is appropriate. Okay, what is the genetic programming paradigm? Before talking about what this paradigm is, I'm going to share the experience that I've had talking to normal colleagues that are not necessarily C++ programmers. So, as you know, I really love not only the generic programming paradigm, but the functional programming paradigm. And when I tell them that I like it, the the thing that I think they understand of what I say is not exactly that there is a theory, a body of work and yeah, full of amazing insights that are helpful to do great software, but they think to understand functional things that work. That I like practices that make things work. And that's disappointing already because there is no option. I mean, if you're a software engineer and your software is made in a way that doesn't guarantee correctness because of the way that the very way in which you do the software, then you're just a threat to society. So that's not an option. So it's like a platitude that they understand that it makes me very frustrated. And I'm sharing about functional programming because when I say genetic programming, it's even worse because people understand genetic programming paradigm as something that doesn't have cleverness, that is generic, that is like any other, that doesn't have uniqueness to it, in particular, not cleverness. And then it plays a little bit with the attitude of fellow colleagues and organizations, big organizations like the biggest organization, the name shall not be named, uh, the attitude that code must be dumb so that the list of programmers can still work with the code. This is a rejection of cleverness that is called showing off or qualified as an evil in many other ways. In general, that cleverness is evil. I have a very big problem with that. And let's see about that. So now I'm ready to tell you what genetic programming ought to mean. We mean to find the most abstract representation of algorithms and data structure, the basic of what we're going to be computing, most abstract algorithms and data structures, so that we can generalize to the maximum. What do we get when we do that process of abstraction and generalization? That when we solve a problem, we solve it once and for all. No, we're not going to be repeating ourselves, and by repeating ourselves, incurring in the risk of making the occasional mistake because we're redoing what we already did, and then something might get broken in the copy. And also something that is quite remarkable, it's the only programming paradigm that I know that allows you to have improvements that are immediately widely taken up by an entire code base. And I want to remind you of the example of move semantics. There are people who wrote perfectly fine software using the standard template library, containers like vector and so on, that had to incur in a small inefficiency of copying because there wasn't any move semantics. Move semantics was invented into the language, and the rules of the language changed so that a lot of things that used to be copies became moves without any extra participation from the programmers. And the world didn't fall. It was so practical that, to be honest, I never ever saw anybody who have had a bug because the code worked with just copy semantics, containers and copy semantics, and the introduction of move semantics surfaced a bug that was a legitimate bug. That the correct code now was broken because things were copied. Things were now moved in some cases where they were copied in others. But transparently, we all got the benefit. If you didn't do anything out of the ordinary, then you probably got the benefit without extra effort. and without extra effort is important. Well, another benefit of the process of abstraction and generalization is that you remove very drastically the specificities, the things that are specific to whatever it is, the stuff that cannot be generalized. And so you have much easier to combine things, much easier composition, which is the primary way in which software acquires infinite value. Because if it's something is truly composable, then you use it very often, and the presence of that thing that is very composable is properly tested, has great performance, and so on. So it helps everything around it. And then when everything around it has more value, then the value of that periphery increases the value of the component at the center of it, because then everybody understands how to use it and so on. And then the value of those components go up and up and up without any limit. That's composition. Also, abstraction invites you to achieve a deeper understanding, and this deeper understanding guides further improvements. And also, the application of the generic programming paradigm cures you, is preventive and curative of a vice that is a cardinal sin in our discipline. Big reveal coming when the time is due. Okay, to do abstraction, which by the way is truly hard, and the reason why it is hard is because you're required to formulate new concepts or improve existing concepts, right? So I am not referring to the language feature of concepts in C++. I'm referring to the natural understanding of the word concept. And well, if you put a lot of concepts together, I think that it ought to be called a conceptualization. So I believe that what Alexander Stepanov did of designing the way of iterators and the powers of iterators, that they are bidirectional, random iteration, etc., this is like a conceptualization. And if it is even bigger, all of the conceptualization for iterations and the conceptualization for containers and so on, then the whole thing ought to be called a theory, right? And let us do a little bit of foresight of my use of the word theory, why I like the word theory. Okay. So then we see that the generic programming paradigm is the opposite of code without cleverness. What you do is to maximize the expression of knowledge into the software code. And because it is knowledge what we're talking about, if you don't have the knowledge, then it's not going to be natural for you to read it. It leads to very strange looking code, even intimidating, because you don't have the concrete data type. You just have like a template argument that you don't really know what that template argument truly means, like what is the concept behind it. Even if you have a Sphinx or the C++ language feature of concepts that establish some restrictions into what are the acceptable template arguments for that concept, that doesn't really tell you what they are. And then the documentation might not be there. And that's so it's tricky. It's genuinely hard. So this leads to my first explanation for why the generic programming paradigm might not be so popular as it ought to be. I believe that this potentiates our skill, okay? Like a base to an exponent. The problem is when the base is less than 1, because exponentiation by a power greater than 1 of a base that is less than 1 is going to go down, it's going to diminish. So I believe that there are programmers out there that are not quite even reaching the level of carrying their own weight in their projects. And the introduction of something like generic programming will make that thing more noticeable. So the generic programming might hurt some programmers. But of course, the generic programming is something that ought to be used because it potentiates dramatically the people that adopt this practice and learn how to benefit from it. So there's a the empowerment is such that it can get to the point in which we literally are able to do things that we would not be able to do any other way. And I'm going to share with you uh, a very important example, one of my most important successes in my career, that is exactly that, something that without the powers of genetic programming, I wouldn't have been able to achieve in any way. Then there is the thing that the tools like artificial intelligence coders are probably devastating the market for the services of our colleagues that are not in the not able to do at least as much as these AI tools. So it's truly important to be way above that threshold, right? But from my perspective, man, excuse me for the lack of modesty, but ChatGPT in particular has only increased the value of my work because it helps me so much that I can do so much more, and then the results are there. We're gonna see momentarily things that ChatGPT has helped me for this very presentation. Okay, so let's a little bit more specific. So we like the principles that we have always used. Minimize coupling, that's undesirable. Maximize cohesion, sure. Genetic programming helps you in that regard too. But one that is far less popular or far less known than the other two, which is orthogonality. I don't want to be defining the theory of what orthogonality is, but I have a good example that is the Unix streams for that. And the Unix streams for data, if let's say that you're consuming data, you're reading, okay, well, you use the API of read in a very consistent way, and you don't care whether you're reading from a device, from a character device, a block device, a network connection, a database cursor. Those things are not relevant to the process of getting read if you only want to read. If you want to do non-blocking read, if you want to do seeking, if you want to make sure that the connection keeps alive, etc. Well, we're talking of a different thing, but the 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 most fundamental use of the data of reading, you can just use the API of reading for that. And then there are the other dimensions that you can think about. Reading has a dimension, an aspect of functionality, and there are other dimensions of, for example, opening a database connection, closing a network connection, opening a file in the file system that require their own unique dimension of operational capabilities. The important thing is that they are not commingled together. Like opening a file does not changes the way in which you read, the ways in which you read, and so on. So this what captures the idea of orthogonality, that progress in one dimension or the action in one dimension doesn't affect what you have in the other dimensions. I mentioned this because genetic programming is, to a large degree, a rejection of the object-oriented paradigm. And the problem with an object-oriented paradigm is that it allows you to have variations on only one aspect, which is the criteria that you're using to refine the subtyping relation that you captured with inheritance. I'm sorry if I am too theoretical at the moment, but I just wanted to be reasonably complete in the explanation. We are not getting to the practical part, but as always, my presentations are meant to be watched live and revisited out of line when you have the opportunity to see it and play back and stop and go forward and backward. So The consequence of the lack of support of object orientation for more than one aspect that varies is that it forces you to impose, to show horn, to jury a hierarchy into every model. Generic programming templates in particular don't have that problem. You can have template arguments that take care of different dimensions of your scenario, and it's perfectly fine. But it's that already have introduced you a really big advantage of this paradigm with regards to a very popular one, which is object orientation. Let's see the example of iterators, because it's a very, very well established concept. And yet, it continues to be somewhat controversial because nobody else did what C++ has been doing since 30 years ago when Stepanov submitted the original proposal to the standards body in 1994, which is, wow, it's 30 years ago. And they didn't follow suit. The other communities of programming languages haven't. And the it begs the question of why, but we have been very, very successful, right? So in any case, I was saying that generic programming is a abstraction and generalization. What an iterator abstracts is the concept of a pointer, and we'll see the generalization immediately. The the pointer has inherent capabilities to them, like accessing data in a data structure. That's what you use pointers for. Traversing a data structure, a collection of elements, a range, what we call now a range, and something quite tricky, which is optionality, because you can always have the null pointer that doesn't point to a valid object. So a lot of people have used pointers to represent the monad of optionality. Like the entirety of the Java programming language uses the monad of optionality by recurring to null references, and null references are obviously um, just a pointer, right? Okay. So if you see, iterators don't replicate the pointer arithmetic rules, and because they don't, they have more nuance in the generalization. There are more specific categories, which are like, for example, forward iterator, bidirectional iterator, random access iterator, and so on. And look at how they replicate the capability of optionality. They don't require a magic value such as a null iterator or an invalid iterator. That's not an invalid value or a value that is special or magic in any way. But what it is done is that because an iterator also refers to a collection of elements, we're gonna de facto create a sentinel, and in particular, we are always going to be able to create a sentinel because even the empty range has one position, which is the position where no elements are. And in that way, every time that I want to mean that there is no element to refer to, then we make the iterator the same as the sentinel. And so there is, to a degree, that dichotomy between having a value, pointing a value, referring to a value, versus the optionality of not having it. Before we get deeper into this, if we talk about a standard template library, about iterators without talking about the algorithms that apply to them, that would be like a clapping with one hand, something that obviously is foolish. I just want you to very quickly observe the comparison of when we have genetic programming versus when we don't have genetic programming, like in in C that the function that does sorting in C is qsort. So in C++, we have some template that captures quite a lot of knowledge of, we call it random iterator for the beginning, for the end, and a comparison function, right? And I will not put the overloads with execution policy and so on because we would lose focus. But in a plain vanilla way, right here, when you, for example, have a iteration over the range, you can have something that has a random iteration, like, for example, a double-ended queue or a vector, typically, or maybe even a plain array or a standard array. So this supports a universe of data structures as long as the iterators are random access, not limited to just an array. Furthermore, the way in which the elements are manipulated internally, because sorting requires you to rearrange the collection. It has quite a lot of nuance into it because it can do moving of the elements in the collection, can do copying of the elements in the collection, and so on, depending on the specific characteristics of the type. And all of those concepts, all of those things are tremendously helpful and very far away from your concern. Like, you're not thinking about it because if your types do reasonable things, then everything works beautifully, composes. In the case of C, well, it is very error prone because you can, for example, typically change the order of the count and the size. And this is catastrophic, but not necessarily readily obvious, because you can have, for example, a unit test in which the collection only has one element, and therefore it doesn't matter if you make the mistake of changing it. And the other problem is that not only you're limited at an array, but the elements themselves will have to have value semantics, and only value semantics. They cannot have any referential semantics to it. So it puts you into a corner in which you have to do things like, for example, wrapping the values with a pointer and then sorting the pointers to the values. But that's an indirection, and you have to create dynamic memory to have the collections of the pointers. It is a world of hurt and pain because you cannot express the things that you express without even thinking in the case of sorting. But I believe that the sort that we understand here has important problems. One of those problems is that I continue to not see at all why they require random access. I went and expressed my disagreement by implementing quicksort that only requires forward iteration, not even bidirectional iteration, but just forward iteration. And I got really great results. And this was the tool that my company, when I was working at Snap, my coworkers used for a big gain that they had. And I reported these at cplusplus now, so I don't need to say it again. Point is that these are perfectible, that improvable, refinable. This is for reference later when you see the slide deck, not for live. There are criticism about iterators, and the criticism is very informative. Like our friend Arno Schurl is going to present tomorrow at this conference why he thinks iterators got it all wrong. And obviously, I am not going to be in agreement with that phrasing. But I can recommend to you guys to see his presentation if you haven't watched his argument before, because he gives you ideas, and those ideas are important for you to make better code. Just the same, there is this presentation by Barry Refsins. It's called Iterator and Ranges, comparing C++ to D to Rust and whatever. And he's skeptical about the superiority of iteration in C++. And I still recommend. So, because what is my guidance with regards to these two presentations? Well, with regards to Arnold shuttles, hold on. What you're criticizing iterators for that includes the duality between referring to an element versus referring to a border, that might come from supporting optionality. And optionality is complex and a tricky concept to grasp and deal with. So maybe what's wrong is that iterators adopted that power of pointers. It's just a question. You answer it, right? But by just formulating the question, your mind begins to do better software already. The case of Barry Racing, one of the things that he criticizes is that the to make an iterator in C++, you had to put a lot of boilerplate, including this very tedious thing of making the flavor of const iterator and making sure that the members are const or wrong const and so on. And I believe that this boilerplate is because there is a failure in the language to support this symmetry. And some other people have seen into this, like Ben Dean, and they have come with solutions to aspect of this problem, like deducing this. So is deducing this the true solution for that particular criticism that Barry Lessin enunciated about iteration, or do we need to do more? Again, the very formulation of these questions and informing yourself of the improvements in the language and so on will naturally lead you to do better software. One of the things that I did for this presentation is that the very corpus of the benchmarks don't use conventional C++ iterators. They use simple iteration that was made specifically ad hoc for you to see what's going on without having to scan and reject mentally boilerplate that is not relevant. So the majority of the empowerment from applying the generic programming paradigm is going to come from you refining concepts. So can you imagine a code base where most of the activity that happens in that code base is to refine concepts? I'm going to tell you a hint. It's going to look very strange. And that's my own repository. And it looks very strange. We have reached the moment for the big reveal number one. The electromagnetic wave progress. Electromagnetic wave progress. What do I mean by that? This is a metaphor. And I need to introduce it by saying that I really believe in the maxim by Richard Philip Feynman, the Nobel Prize winner in physics, that mathematics is organized reasoning. That's what I refer to as mathematics. So for me, theory, mathematics are the same thing. It's organized reasoning. So we're talking about electromagnetic waves. Light is just electromagnetic radiation. And electromagnetic radiation is because electric energy is being propagated in waves. Why? What gives rise to electromagnetic waves then? Very simple. A change. Let's say that you have an electric field changing in this plane. A change in the electric field induces a change in the magnetic field. And that change in the magnetic field ends up making a change in the in the electric field that makes a change in the magnetic field that makes a change in the electric field. And there you go, voila, you have a wave propagating. Now, if you substitute the word of propagation by progress, because you can think that there is a desirable direction, a desirable direction of progress of making better software, you substitute magnetic field by theory. And mind you, the magnetic forces cannot make work. So like the theory on its own is not going to give you practical benefits. You substitute the electric field by the practice of software engineering, then you're going to see that an insight in the practice induces an insight in the theory, and if you keep iterating and being earnest about it, the insight in theory gets expressed into an insight into the practice, and you have the flywheel of progress. The problem is that when you go from what you learn from applying something in production, let's say, to a formalization, you organize in your mind what was the essence of the success. You're basically building a theory that is a solution in search of a problem, and that's when you lose the sponsorship. So it's very important that you understand the value of doing it, because otherwise, when you don't have the sponsorship, you're not going to do it. This analogy is good because it holds to even closer inspection. In this repository that Scott, Jamie, and I were working, we are iterating very tightly on the practice gives us a better understanding of a concept, and the concept gives us a better practice, and so on, right? Very tightly. I would say like the people that work changing the language work 2 orders of magnitude on a longer period. And so for us, the reality, sorry, the going from theory to practice happens on a regular basis. We see it several times per day. But when you hear people changing the standard library or the language itself, my goodness, I need to hurry up. The problem is that people don't readily see the way in which theory becomes better practice. But of course, the people that change the language overcome much tougher obstacles than what we could in any sensible way. So one book that inspired us to do this is the book From Mathematics to Genetic Programming by Stepanov. And I think that that's like a misphrasing, because genetic programming is from mathematics to code and back, from organized reasoning to code, to expressing reasoning as knowledge code, and back to organized reasoning already. So now we're going to show you some benchmarks, right? I have been talking a lot, as always, but do I have any substance? So we just wanted to make sure that our methods were going to lead to reasonable results, something that was at least comparable, that would match the results of people that put a lot of effort into performance-sensitive things. And what we wanted to do was something realistic, but very well constrained, very small, so that the analysis of causality of what drives things would be easy. Hopefully, we expected to have something important, and we were comparing ourselves to real world production code, hopefully important, and we prepared that for this very presentation. We did not expect to beat anything, because our code is deliberately generic in the pejorative sense. Like we wanted it to not have something special. What we were doing was to demonstrate the methodology more than the how clever we can get with code. However, I honestly think that we cannot say that we matched the results, because we blew past them. Our results are truly impressive. So the benchmark that I'm going to show you real quick are hopefully very representative of what you do by iterating the electromagnetic wave. And it's going to be the string functions of string length and A to I, the conversion of ASCII to integer. This is the glibc in particular runs the world. So you cannot have something more meaningful than comparing yourself against glibc in particular. And this is not even something that plays to the advantages of our framework. It's just suitable, compatible. My framework, our framework is usable, is applicable, more than especially good. These are the results that we have for invoking the functions in benchmark. So what we're going to see momentarily is that when in the code, in the benchmark result, we mentioned glibc, we report the results for that function. Um, in the case of the string length, AVX2 and a neo assembler, those are the implementations. And also the one that doesn't use the SIMD registers, but it's like the generic portable version, we call it the generic glibc implementation. And when we talk about the SU, they are going to be string length is what I believe is the most performing one. Natural is like the most straightforward way to express a string length. And the AVX and Neon is obviously using our methodology, not necessarily our library, but our methodology to arrive to exactly the same clone or calc of the SWAT library string length, but expressed with Neon or AVX intrinsics. So these are the results. In the case of a string length, glibc string length is worse than the SU implementation of string length that uses SIMD, the apple to apples comparison gives that the SU implementation is more than twice as fast. More than twice as fast. In the case of the generic non-SIMD, both versions of the SU string length are about twice as fast. That's why I say that we didn't match the results. We blew past them. And this is the time in which I switch, has advertised, to the Compiler Explorer. The only problem is that, of course, I have been talking so much that I am exhausting my time quota. But let me show you, for example, this doesn't have the Neon implementation because it is compiled for, it was pre-processed for in my machine that is an Intel machine. So let me change here and okay. So this is the implementation of string length. In terms of source code, I hope that you are able to see the code from the pane in the presentation. And all I want to do is to show you that the thing is more or less natural. Like what we're going to be doing here in all of these functions is, all of these functions, plural, is we're going to try to make it so that the loop invariant is to consume or process a complete block of data. And to arrive to the loop, we have the problem of misalignment. So we fill in the block of data with data that will not make a difference for the result. In the particular case of a string length, we fill the block with bytes that are not null. Then we do the core of the loop, which is using techniques to detect the presence of a null in this particular case. And I use this trick of subtracting the block of bytes to a block that contains only the number 1. And believe it or not, that's going to borrow right after the first null. So that's how it's right in the first null. So that's how you detect it. And then you detect whether there is a null in here. And if we saw one of them, then we saw, oh, okay, the loop invariant is broken. We take into account the partial result when the loop invariant was broken, and we are out. And that's all that happens, right? So rebuilding code. So here is the entirety of a string length expressed with our library. And I want you to notice the fact that it only has one conditional branch. And that conditional branch cannot be removed because in the case of a string length, who knows when the null byte is going to happen? We just had to iterate until we find it, right? So this is boiled down to its minimum expression. And the AVX version is just the same. But just out of kicks, I am going to show you in the implementation of the same function of a string length using the AVX2 platform. This is the assembler, okay? So you can go on your own and check this, but you can follow my guidance with regards to this impenetrable code or nearly impenetrable code that these guys are doing loop unrolling of 4 iterations at a time and so on, right? And you can see that they have put a lot of effort into doing it. But why does it happen that our code basically because it is you'll have to take I'm sorry about this glitch on my slide deck. So the AVX function is basically the same that I just showed you of building the invariant. And as soon as the invariant is broken, complete with the partial result that you have and get out. So this doesn't have anything mysterious to it. That's why I meant by genetic, right? Yet, according to all of the benchmarking that we have done, it is more than double as fast. So at this point, I am going to abruptly change the presentation to give Jamie the opportunity to show us the result of the benchmark for the ARM platform because he uses a Apple M1. And if you are ready, Jamie, then this will be the moment for you to start a part of your presentation, please.
All right. Thank you very much.
Jamie is working in a startup in the Los Angeles area. And I forgot to mention that. Terribly sorry about running out of time.
Okay. You guys can see the presentation correctly?
Yes.
Okay, great. There's a window in there. Okay, great. You must put this window in the middle, which I don't need. Okay, right. Okay, thanks. So yeah, here are the results of the of running on this ARM machine right here. And as you can see, it's very comparable, and you can see that the power we get in Intel world translates just the same into good optimized.
Jamie, I'm terribly sorry, my friend, but we've run out of time. Would you please focus on the neon part?
On the neon part. Uh,
Yes.
sure. So, yeah, we can see the neon benchmarks here. Um, uh, the benchmarks are much more performant than the glibc. It's by
Could
an order of magnitude there. I don't know if you wanted to touch on anything else there, Eduardo.
yeah, so we can read out loud that when we invoke the corpus for neon implementation, the SU neon, it takes 3 microseconds and a half to scan 1,031 words or strings, but the use of the string length that comes with libc takes from 3.5 microseconds. We're talking of over 5 microseconds for the implementation of libc string length. And the same thing happens with the implementation of ASCII to integer. If you see ASCII to integer is more than twice as slow as the SU implementation, and you can see the code on your own. The code is already in the main branch, and it doesn't have anything mysterious. It's the very same implementation. Um, Jamie, I think that we don't have the time to do the part on associative iteration, but I believe that we have been able to drive the point home. Now we're going to get Scott an opportunity to say hello because unfortunately I ate your time, guys, and it is entirely my fault.
So typically in C++, we think of a list or a container being sortable, meaning something like having a strict weak comparator defining its ordering. We typically use a sort interface, something like sort begin, end in the comparator. There's some different interface we can use that might result in us being able to allow our tooling to make a better choice for us or allow us to get a better runtime for our sorts. So first, we want to think about comparators that are mostly of the form. Usually, there's no complex thing going on when comparing the weights of two elements. Usually, the comparator reduces to something like compute the weight of the left element, compute the weight of the right element, then compare those two elements. To do this, we have to compute the weights repeatedly. For complex comparators, computing the weight is very expensive. And if we compute the weights twice per comparison, the n log n sort of turns into n log n times the cost of the comparison times 2 times the cost of computing the weight. This feels expensive. It feels like we're doing extra work. So there's an alternate sort interface we can consider. Less than in the comparator will always be the same if we arrange the weights to return in sort of ascending order. If we make the weight functions, or if the weight functions naturally give us something in descending order, we can obviously just invert via use of the negative. So then we have an alternate sorting API in which we simply provide the beginning and the end range of the begin and end of the range, then provide a weight generating function. This interface might allow us to pay significantly lower costs for generating weights. There's a thing called decorate sort on decorate, which basically computes the weights, decorates each element with those weights. We then sort the weights as opposed to sorting the elements using a comparator and then shuffle the original list back in a sorted order. If we do this, then we only compute the weights n times as opposed to n times log n times 2 times the weight times. This results in material savings and cost sometimes. Using a weight that is compatible with radix sorting also results in a material speed up. This requires a little bit more difficult computation or a little bit more difficult coding, but results in a big O time of only n. So if we have a comparator that's heavier than a simple less than, likely the function call overhead will be so large and the cost of computing the weight function so expensive that it will outweigh the cost of a simple memory allocation and shuffle post sort. If the list is small enough that we can compute or that allocating and computing a list off to the side of weight, comma, index, then we're likely to see a benefit. In the case in which we have, 100 billion elements that we're sorting, these sort of techniques will not be advantageous. In the case in which we have a comparator that is so light that it is nearly equivalent to less than, this technique will not be advantageous. But anytime we're using a custom comparator, it is likely that the comparator will be heavier than a simple less than, to such an extent that doing that computation less will be of a huge advantage. So why is generic programming and SWOR relevant here? So generic programming will allow us to have our tooling make more choices about the optimal usage of which sort algorithm approach we can use when we're using the weight API. When we use an API that takes a comparator, then all we can really make a choice on is like which broad category of sort algorithm do we use? Do we use a quicksort? Do we use a merge sort? Do we use a heap sort? If we are using the weight API, then we can actually make choices about using decorate, sort, undecorate, using a erratic sort, or using some other method of arranging our sort. Then if we use the SWOR library, then we are able to do more than one compare or compute more than one weight at a time. And that doesn't improve our algorithmic complexity, but it does provide a better constant on the growth scale of our algorithmic complexity. All right, back to you, Eduardo. I tried to go very fast.
The big reveal number 2 is that the NAS device, the capital C is over specification. What our colleagues that have been working on the glibc library have done is that they have specified so much more than they needed to that they put the actual microprocessor in a bind. The microprocessor needs to execute what they ask it to execute explicitly. So if they unroll 4 times AVX registers and so on, the microprocessor needs to execute that as is. Our formulation gives maximum freedom to the compiler, maximum freedom to the processor too. Therefore, they come to bear much more aggressively and they help us. And this is truly critical for the purposes of benefiting from the generic programming paradigm, which is give yourself as much room as possible by erring not on the side of specifying too much, but perhaps specifying too little, however ironic or counterproductive that might sound at this stage. Well, friends, thank you very much for your attention. It has been a pleasure to share the time with you. What ended up happening is that I got very excited about the material that I was able to share with you, and then the efficiency of the speed wasn't high enough.